couple things I just want to talk about, or actually just one main thing I want to talk about before I turn it over to Phil. We just, unfortunately, in January, we lost a longtime board member, Ray Kadingo. It's because of Ray that I'm here. He introduced me to the Maria board and encouraged me to join. And I'm glad he did. So we've lost a friend, we've lost a wise man. He helped Maria a lot through the years, and he certainly will be missed. One of the things that Ray was a champion of was, and some of you probably know this, he was planting trees. He started a group to plant trees all over the region, and he's probably responsible directly, indirectly for hundreds, if not thousands of tree plantings. Because of this, and in Ray's honor, board members are spearheading a project to plant a grove of trees in his honor. So with that, I'll turn it over to Phil, who will give us an update on upcoming events. Phil?
Oh, great. Yeah, I just want to make sure everybody's aware that on February 23rd, which is the next month, the last Tuesday of the next month, which is when we have our live presentations, our topic will be how to build a better fire. And that's a topic that combines two speakers. One is speaking about industrial use of wood in applications for use in heating and other forms of power generation. And the other person will be speaking about home fires and how you can have a more efficient home fire. This has been kind of a controversial topic that we've been dealing with ever since in the early 1990s. They decided that it was considered, wood was considered a renewable fuel. And while it has some benefits over other forms of fuel, it also has some drawbacks that are significant. So we thought it was really a topic that needs to be explored both from the positive and the negative side of it to better understand it, but then more importantly, what can we do about it? A lot of people are burning wood, so what's the best way? What's the best way to build a better fire? So that will be on Tuesday, February 23rd, the last Tuesday of February, and same time, 7 to 8:30. Then in March, we're going to have a book discussion on March 11th on a book that is also available in a Netflix film, A Life on Our Planet, which is David Attenborough, who I'm sure many of you know from seeing some of his Life on Earth, The Living Planet, The Blue Planet, a number of just beautiful documentaries. And he's had an interesting life, and as a result of that life has been exposed to a lot of things that have brought the issues of where we are in our stewardship of the planet. And he offers a kind of a scary witness, but follows that up with some very hopeful and thought-provoking things that we could do about it. So that should be an interesting book discussion. We'll be very interested in your feedback on that. And that's on March 11th. That's a Thursday from 6:30 to 8 p.m. And the information for both those are on the website. And we will be having a meeting in March on the greening of hydrogen, which will be the last Tuesday in March. And we'll have more information on that, and there's more information on the website right now. So with that, I'll turn it over to Chuck. Is that correct?
Good evening. Welcome to the monthly Maria meeting. It is my pleasure to introduce two speakers this evening. Both have association with the Villanova University curriculum in sustainable engineering. The first speaker is a graduate of the master's program in sustainable engineering. Her name is Karen Hegerman, and she is currently the program manager with Sustainable Packaging Coalition, which is a membership-based collaborative run by an environmental nonprofit, Green Blue. Prior to doing her graduate studies at Villanova, she got a BS degree in aerospace engineering at the United States Naval Academy and is a helicopter pilot and officer in the U.S. Marine Corps, where she served in many different leadership positions. She has an absolute passion for sustainability, is an avid hiker, and a committed trash picker-upper. And with that, without further ado, Karen, hopefully somebody has allowed you to be a co-host so you can share your screen, and Karen's actually going to tell us what she did for her master's thesis while she was a student.
Great, thank you for that introduction. Hello everyone, I'm very excited to be here and to be sharing my research with you all. So I will go ahead and share my screen. I think I need permission.
If you go over to the right, there you go.
There we go. Yeah, great. All right.
Sorry for the delay.
No worries. It wouldn't be a Zoom meeting otherwise. All right. I'll bring up my slides here. Can you see my screen all right?
I see Mount Fuji.
Yeah.
Okay.
Exactly. There it is. All right. So yeah, I appreciate the introduction. I'm Karen Hagerman. I recently graduated from Villanova University doing the Sustainable Engineering program. I just completed it in December, and this was my thesis research, which I'll be sharing. And like any good thesis, my title was long and complicated. It's a whole systems assessment of the polymer value chain and recycling infrastructure in the US. But what does that really mean? It's simply just plastics and plastic recycling. And I'll kind of go into why it has that more complicated name. But I really just want to share with you my research process as well as some of the highlights of the results. And so some of what I'll be going over again is the background problem that I was trying to address, and then my methodology as well as the results, and then a really interesting look at the systems, the whole system that incorporates everything to do with plastics and plastic recycling, and then some of the key issues as well as the conclusions that came out of my research. So I'm sure with this group, we've probably got a fairly good knowledge base on the issues with plastics right now and plastic recycling challenges, but I'd like to just kind of go over some of the background that fed into my research. And so one of the things that you notice in the title, I refer to it as polymers. And so polymers, most of the time when we think polymers, we think of plastics. Polymers are large molecule chains that are composed of repeating monomers joined together in a process called polymerization. There can be natural polymers that exist out in nature, also synthetic or man-made polymers as well. Most of what we think of as plastics is petroleum-based, about 99% of what's on the market, and that's usually from a crude oil or natural gas source. There are also bio-based polymers, and those are increasing, although again, they're only about 1% of the current market, but they're growing in terms of applications and different sources for that bio-based raw material. These come from different biomass sources like, for example, ethanol from corn. There's also an important distinction between recyclable and biodegradable polymers. Not all bio-based polymers actually biodegrade. Some have a chemical structure that allows them to be recycled with petroleum-based polymers. And so I wanted to look at all of the different types of polymers and assess the system with the knowledge that the future is going to have more than just synthetic polymers in it. It's going to have a lot of these bio-based polymers. And so whatever changes we make to the system, we really want to incorporate a future that can handle and process the increase of bio-based polymers as well. In terms of recycling in the US, so the recycling of synthetic polymers really began in the 1970s. And there was a growth of curbside services that began in the 80s and 90s. And then towards the end of the 90s and into the 2000s, there was a real push to shift towards single stream recycling, which is the collection of all materials together, and then they're taken to a material recovery facility and sorted there into the different types of materials, and then sent for secondary processing and where the actual recycling occurs. And so these programs are run primarily at city or municipality levels. And because of that, there's a lot of disparity in the types of materials they collect, and as well as the way that they process the materials or where they send the material. An important factor to consider when we're talking about recycling, especially plastics recycling, is the role of China in the global recycling market. And so China really started taking an active role in recycling in the 90s. And it was really the expansion of globalization, the interconnectedness of supply chains. China recognized that there was a market for buying exported waste from other countries, importing it and processing it near where the factories were that were actually using that recycled resin. And so because of this, the United States started shipping a lot of our waste overseas. And as a result, the processing infrastructure within the United States didn't develop during that time because it was more economical to send the waste overseas. However, beginning in the 2010s, there was a lot of shift in Chinese import policy, most notably in 2013, the Green Fence policy, which required increased standards and inspections on imported waste, and then the National Sword Policy, which was introduced in 2018, and that really limited certain types of materials being imported as waste to China. And most of those, a lot of that was the different types of plastic that were restricted from being imported. And it also lowered acceptable contamination rates within the waste that was imported. So concurrently with this huge shift in the global recycling market was this growing awareness of the issue of plastic waste. And I'm sure we're all familiar with it here. It's been, in the past 5 years especially, making huge headlines. There's been research and reports showing the enormity of the issue. We've got the Great Pacific Garbage Patch, among with other gyres that are collecting waste in huge patches in the oceans. And then there's also a prediction that there will be more plastic in the ocean than fish by 2050. Also, the startling fact that over 8 million tons of plastic enters our waterways and oceans every year. And so all of this is really feeding into not only the public awareness of the issue of plastic waste, but also a growing pressure on brands to do something about this issue, particularly brands who make, produce, and sell plastic products. And so because of that, there are brands that are committing to address recyclability and plastic waste through certain commitments like the Ellen MacArthur Foundation's New Plastics Economy and the US Plastic Pact, which was just introduced this year. So all of that kind of fed into the background and basis for the research that I wanted to do. And there were several key aspects of the problem that I wanted to address. The first being the actual plastics recycling rate. So it's becoming a more widely known fact that the amount of plastic recycled in the US is really close to, if not lower than, about 9%. But it's actually likely much lower than that because a lot of that data is prior to the full impact of the Chinese import ban being felt. And additionally, there's different rates within different polymers. So polymers like PET, your traditional plastic water bottle, or HDPE, which is your milk jug, those get recycled at a much higher rate than others like polypropylene, which is like a yogurt container, or polystyrene, which we all know in its expanded form as styrofoam, and then a lot of plastic films, which are recycled at a much lower rate. There's also a lot of disparity in terms of what plastics are accepted, and this can differ from one town to the next. And so there's a lot of consumer confusion. The chasing arrow symbol on the bottom of your plastic package means very little in terms of whether or not you can actually recycle it in your recycling system. And so this leads to a loss of recyclable materials and also contamination within the plastics recycling market. Additionally, there's a really big push towards circularity. So there are brands, again, the ones that are feeling the pressure, they're committing to being more circular with their materials. So keeping the material within their production loop and not losing that to waste or to the environment. However, as part of this, a lot of brands are committing to using 100% recyclable material, which is, it sounds good in theory, but if we don't have the infrastructure to actually recycle that material, then the intent behind this circularity shift is not being met. The other issue, when we step back and look at it from a wider sustainability perspective, is that the whole impact of the value chain isn't necessarily being assessed or isn't even known. For polymer or plastic recycling to actually achieve sustainability goals, the system has to address issues that go way beyond just technical capability or economic feasibility. It needs to address issues like the impacts of non-renewable resource extraction or polymer production processes, or potentially necessarily understanding the impact of leaked waste into the environment and what the consequence on ecosystems as well as human health is. And those things aren't fully known at this point. The other thing that kind of fueled my investigation into this issue was the fact that a lot of the existing literature out there focuses on one small aspect of the value chain, like the specific type of new polymer that could be produced or a specific technology that can address how to recycle films. But there's very little in terms of looking at it from a whole systems perspective. And so one of the things that I think is fantastic about the Villanova program in sustainable engineering is that we take this whole systems approach. And what that means is looking at it from all different aspects and all different stakeholder points of view. And so we use the acronym STEEP, and that stands for social, technological, economic, environmental, and political. And so really looking at all of those issues and how the different factors within a system and how they're all impacted from different stakeholder points of view. And so that's what I wanted to do with my research. So the objectives for my research were to conduct this in-depth exploration of the current recycling infrastructure, to develop a comprehensive systems map to better understand everything that was going on within the recycling value chain, and then to apply this STEEP methodology, this social, technological, environmental, economic, and political, to examine the issue from the whole systems perspective, and then be able to identify areas for systems improvement within the system. So for my research, what I did was collected a large amount of literature, really everything that I could find that had anything to do with plastic. And I started out just looking at academic literature, but I soon found out that that wasn't giving me the whole picture. It was, again, studying little pieces of the value chain, but I was missing a lot of the social aspects and even the environmental and economic aspects. And so I broadened my scope to look at industry publications, government reports, and NGO research that really helped to build out that whole systems perspective. I got to see different takes on the issue, different perspectives, different focuses within, and then also a big thing was access to information. So some of the industry publications have much more recent data on the economic aspects. Some of the NGO research has a lot more investigation into the social impacts or the actual quantitative environmental impacts. And a lot of that came out in 2020, and I was able to take that recent data and really analyze it to build that entire picture out. And then briefly going over the research process I used. So I basically collected all of that information from all of those sources I could find, and then I started to just pull out all of the data and group them into those 5 STEEP categories. And once I had all of the data collected, I started sifting through it to see if I could consolidate similar data from different sources into these independent factors. And so once I had these factors, I connected each factor with the top 3 stakeholders that were either impacted by or could have an impact on that factor, and then also connected it to different elements in the systems map, which I'll show in a few slides. And then I assessed the factors as to how positive or negative their impact was. And then from there, I was able to kind of analyze the results and then put it back into my systems map and visualize it and start to identify the real big issue areas. So for the assessment, and I know this is difficult to read, it's not intended to be read, but just to show you that in order to assess it, I developed a rubric that allowed me to basically put different criteria in the 5 different STEEP categories, because an extremely negative social impact is not really the same thing as an extremely negative technological impact. And so I defined those, but overall it's the scale from extremely positive to extremely negative. But one thing I do want to point out is that the +1 and -1 are reserved for either risks or like potential positive. And that way I could weigh the impact of a potential risk or potential positive impact, and they wouldn't be assessed the same as a actual impact that was occurring. And to kind of give an example of what I mean by a factor, so for this example, an economic factor is recycled resin prices are increased by the cost of processing and transportation. So that was the factor that I distilled from the data that I collected. And you can see it was 3 different pieces of data from 2 different sources. And overall, according to when I applied my rubric to it, it was a -2 score for that factor. And then I tied that factor to the impacted stakeholders. For this example, it's recyclers, product manufacturers, and plastic producers. And then I also tied it to 5 elements in the systems map. So moving on to the conclusion or the assessment results, the overall score is -166, which sounds really bad, and it is, but without having applied this type of methodology to a different system, we don't really know what that means. We know that it's bad. You probably could have all told me that you'd expect it to be really bad without even, doing this assessment. And so what I think is more interesting is looking at the results and the breakdown and distribution. And so on the left side with those icons, you can see the breakdown by steep category. So social and environmental were the most severely negative, and the economic category was the only actual overall positive one. But I think what's more interesting than overall results is the distribution. And so that's what you see in this bubble chart. It's showing you on the left, the y-axis, it's +3 to -3, which is the most beneficial to most severely negative factors for the assessed value. And then we've got the 5 steep categories. And so you can already start to see that there's an interesting distribution that doesn't come across in the total scores. You can see that the social and environmental and political impacts are definitely skewed towards the negative, and there's more negative factors there than positive. However, if we look at the technological and economic, we see this wider distribution of positive and negative factors, indicating that there are actually some significant technological and economic benefits occurring or present in the recycling value chain and recycling or the plastics infrastructure. And so because the way I did the data, I could also break it down further to see what the sources were telling me. So I could actually see that if you look at the dark green, that's the NGO, the almost brownish color. Those are factors from NGO sources. And so you can see, as would kind of be expected, that the NGO literature tended to focus on social impacts and environmental impacts, whereas that teal color, which is more significant in the technology and economic, that's industry data. And it makes sense too, because industry is providing a lot of data on technological factors as well as the economics of recycling. And so you can start to interpret that. That way I could draw conclusions that weren't necessarily skewed by where the source was of that data. I also broke it down a little further, and I won't go too far into this, but I was able to break it down to see the impacts on each stakeholder in the value chain. So these are the top 8 stakeholder groups I identified. We've got waste management companies, polymer producers, recyclers, product manufacturers, consumers, governments, local communities, and workers. And I was able to break it down to see how it changes when we're looking at social aspects. So you can see consumers are really significantly impacted. You also see here that waste management companies are impacted by social, and that's really because they're kind of the connector in the system. They're the interface between consumers and local communities and the rest of the recycling chain. So they're really connected to those social impacts and really have the ability to influence it. And we'll go through all of them, but one of the most significant conclusions that I drew from this is you can see the lack of data on workers. It's interesting because workers are involved in every aspect of the value chain, but there's not much literature really describing the impact on them, especially in some of the categories. There's very little representation at all. And so moving into the systems mapping, so I know this is a lot to take in. This is the overall systems map that I developed using all of the data that I uncovered and did through my research. And so what you're looking at is a traditional stock and flow diagram. And the green boxes are stocks in the system. So a stock is something, a quantity of something within the system. Then the hourglass shapes are all flows. And so those are factors that, or those flows affect the rate of increase or decrease into the stocks. And then on the left side, we've got the sources, and that's where material comes into the system. And on the right side on the right side, there are the sinks. That's where the material exits the system. And then everything else, all of those other words are variables that impact the flow within the system. And so all of these can independently influence the other factors, and some are connected to each other and some are dependent. And so it's a very involved and integrated system when you take a look at everything that really goes into it. And so just a brief overview of what you're really looking at in terms of the plastics value chain. You've got coming in the top left, both renewable and non-renewable resources. Those get processed into polymer resin. That polymer resin is then used to produce plastic goods, both durable and non-durable or single use. And then from there, at the end of their useful life, those products are disposed of and become waste, potentially recyclable waste. After that, there's several paths that I can take. Of course, it can be leaked into the environment, becoming plastic pollution. Some biodegradable plastics can be composted and turned into biomass. And then a large majority of the waste is transferred to landfill and either buried in a landfill or transferred to incineration, becoming atmospheric pollution after that. For the material that actually does make it into the recycling system, it goes through that material recovery facility and becomes sorted plastic waste. From there, it's treated, it's typically separated. The majority has been mechanically recycled. However, there's been a growing use of advanced recycling, or what's also known as chemical recycling or feedstock recycling processes. And so those are two pathways that plastic waste can take. There's also some plastic that's converted directly to fuel and combusted, or chemical feedstocks from that chemical recycling that is used for fuel production or used for non-plastic applications. The material that does make it through recycling then gets processed back into a form of polymer resin that can then re-enter the production system and be reused for its second life. And so all of these elements within the map is what I connected the factors in my system, in my assessment to. And so I was able to see which parts of this system were really the keys to addressing the issues, and then also which parts of the system were really working well and benefits. And so what you're looking at here is the same systems diagram as on the last slide. So if you flip back, it's this same systems map. Everything's relatively in the same position. It's slightly moved around, but it's kind of the same overall layout. But what I've done is now everything's a circle, but it's telling you two things. One, the color of the circles are indicating the total score of the factors connected to that element. And then the size is indicating the number of factors connected to that element. So in the top left, you can see significant issues with that non-renewable resource input arm. So you've got non-renewable raw material extraction and petroleum-based polymer production. Those are the most severely negative in the system. But you can see the size of the collection programs bubble and the MRF processing bubble are bigger, indicating that more factors are really connected to those. What I think is interesting, one of the biggest takeaways you see is that the significant negative impacts are all really across that top, top part of the system. So that's the non-renewable resource extraction and production and processing, manufacturing, and then disposal. Whereas the benefits really only occur when we get into that bottom half of the system, which is when the material actually gets into the recycling system and it can be used and processed and returned to become new material. And the big takeaways you see are, especially with collection programs and MRF processing, those are really the gateway elements that either help the material get into the system or potentially prevent those materials from getting in the system if there are issues with it. It's also important to note, though, that within the recycling half of the system, there are still significant issues like quality, the quality of recycled resin, the current challenges with mechanical recycling, being able to process some of the materials that are on the market, and then other ones like contamination and the comparative cost of recycled resin to virgin materials. And then we can also see that there are some pretty beneficial aspects within the system. So the end market applications is a big one, and it's a growing one. And then also the current demand for recycled resin, especially with those brands who are making commitments. And so you can see that there are definitely positives, but overall, it's a really good visual to show how the negatives outweigh the positives and where those negatives outweigh the positives. And the interesting thing when I started looking at those key issues is how interconnected they were. So obviously with a system, I realized they were interconnected, but when I identified the top 2 or 3 most significant issues within each of the 5 steep categories, I just saw all of these connections that really reinforce the fact that this has to be addressed as a system in order to find solutions. And so what you're looking at here is those top 2 or 3 issues within the steep categories and the connections between each one. So for example, one of the significant social issues is this lack of access to curbside recycling. Over 40% of households in the US don't have access to recycling, and those that do have a very inconsistent access in terms of what types of material they can actually recycle within their system. And by and a result of, and also feeds into some technological issues, like the fact that there isn't integration between design and end-of-life management. And so there's so many products on the market that consumers aren't able to process or have anywhere to dispose of besides the trash. And then there's a lot of, again, non-standard processing capabilities in terms of what's available even within the US. The fact that we don't have access to curbside recycling really impacts a lot of economic issues as well. So one of the big things is that the cost effectiveness of recycling relative to landfills is a little bit prohibitive. Actually, a lot of it prohibitive in a lot of municipalities. It just makes more sense, especially given the low price of virgin material. It makes more sense to landfill a lot of the plastic waste. And then from there, when we don't collect enough, now we have a deficit of post-consumer resin available to meet the demand for brands. We also have lost commodity value of all those plastics, all of that material that we're just allowing to leave the system. And then that ties into significant environmental issues like the large amount of mismanaged waste, as well as the overall one, that big circle, is a political issue of the fact that we don't have any federal recycling policy that really addresses any sort of recycling infrastructure or extended producer responsibility or recycled content requirements. And so all of these issues are really interconnected. And so I'll just kind of conclude with some of the overall, what I pulled out of all of this research and some of the big things that kind of stood out to me. And so there are a significant amount of concerns within the system. Some of the biggest ones being the disconnect between when products are designed and what end-of-life technologies there are available. And that's one of the big reasons we are in the situation we're in, is because the pace of technology, particularly that of packaging technology, has way outpaced the ability of processing technology to actually deal with those materials. And that also feeds into collection and sortation capacity and the ability to manage the sheer amount of waste that we are producing. Some of the issues significantly in that non-renewable material production arm of the system really have significant impacts on human environmental health, as do a lot of the disposal processes. And then again, there's a lack of adequate policies that really address any of this. There are, though, opportunities within the system, those green elements that I showed you. There's a lot of promising work being done. There are end markets that are developing at a rapid pace to address these problems. And so an issue there is really just investing in those end markets and getting those to scale to be able to really handle the waste that is being produced. And then the other opportunities are brand commitments and investment in infrastructure, and then that advanced recycling applications. There's a lot of new work and technology to recycle previously difficult to recycle materials. And so the clear way forward is to really address this as a system, not to have an individual producer working on a new way to or a new plastic that's going to solve everything without really addressing whether or not the applications make sense for the product, whether they match with a certain distribution or a disposal process. So really taking that collaborative and systems approach. And some of the kind of recommendations that I have in terms of research that we should really focus on was one, better technology within sorting facilities to identify and sort plastics. We really have the technology currently is not able to identify the different resin types adequately enough to prohibit a large amount of contamination. So that's a really big issue. And then really looking at both advanced recycling technologies on one side, and then also producing bio-based polymers that are more easily composted or have a better life cycle impact as well. And again, collaboration, especially when it comes to product design, value chain-based partnerships where different elements of the supply chain are working together to find solutions, and then ensuring that whatever policy is developed takes into account all stakeholder perspectives so that it really is the most effective in affecting change. And then there's a lot of investment that is required, and it's encouraging to see a lot of companies are already doing this and working towards enhancing collection programs. And then another interesting thing is the need to scale compost infrastructure, because it's, again, great to say, well, we can transition everything to compostable plastic, but right now our compost infrastructure in the US is even in a worse state in terms of access than our recycling infrastructure. And then the last thing being really scaling advanced recycling technologies, especially the ones that we've identified are a great match for the necessary materials in this system. And so that concludes my presentation. I think we're going to do the questions at the end, so I would be happy to answer any of your questions at that point. And again, thanks for allowing me to share my research.
Thanks so much, Karen. So Ross Lee has joined, but I think his name is Phil Jones, so I'm not sure.
No, it's corrected. He's down here.
Yeah, it's corrected now.
Okay, are you?
I'm here.
Hi, how you doing?
Good. Hello, everyone. Welcome.
Are you able to share your screen?
Sure. I will share my
So
screen.
while Ross is sharing his screen, let me introduce. Ross Lee is the advisor of the lady you just heard speak, Karen. She is one of 60 of Ross's master's students that he has been an advisor for. In the 10 plus years he's been associated with the Villanova Sustainable Engineering Program. Prior to that, he retired from DuPont as the director, Ross, what was it? Director of
Technology, New Business Development.
Technology, New Business Development,
New Business Development.
Packaging. So Ross now the program has moved to having PhDs as well. And Ross is advisor for 10 PhDs. So 10 PhDs, 60 master's students. He's to provide some information on the circularity and plastics, which is a wonderful follow-up to Karen's talk on a deep dive into circularity and the importance of looking at all the stakeholders. So without further ado, Ross, floor is yours.
Thanks. And thanks for this invitation and for letting Karen and I join you tonight at your January meeting. As I told Chuck, it's hard to say no to things that you're passionate about. And I'm sure you heard from Karen's enthusiasm. She's passionate about that area, and I am also. So we're going to talk about plastics and the circularity challenge. You heard about a beautiful systems mapping of a polymer recycling system and the issues that we face because we haven't been looking at it in the past as a system, and how do we start to change the system and move it into something that is right now linear and hurtful to the environment into something that's circular and non-hurtful to the environment. So we're just going to talk a little bit about the overview of plastics and polymers, focus on just three really key examples to show you the value of those materials and talk about how we might get them into more of a circular system. and then talk about where we think things are going. So this is a terrific reference. This is just a way to look at the magnitude. And from now on, I'm going to talk about them as polymers. So all of you think about plastics, but plastics really don't describe them as what they are, which are polymers. And not all polymers are bad, not all plastics are bad. You can have actually natural polymers, and you can have natural materials that behave very much like what you would call plastic. So a lot of times people have gotten the connotation of a plastic as a synthetic material that can't be, it survives for a long time in the environment and causes problems. That certainly can be very true with the synthetic polymers we've made. We'll talk about that. But for now, we're going to talk about polymers. And what does polymer mean? I'll just give you the example I use in my sustainable materials class when we introduce the term polymers. And even though these are bachelor's engineers, some of them really haven't had the focus on what a polymer really is. So the way we do it to really solidify the concept of what a polymer is we have the whole class stand up and we look at each of our arms as potential ways that we might connect. And as we stand up with just our hands, we jump around and we do all kinds of cool stuff that we can do just as individuals, bouncing around, jumping around. And then I tell the class to join hands, and the whole class zigzags all the way around and we join hands. Now we're a polymer chain, and now we try to move around, and we can't move very far. But if something was to try and get through us, we've got tremendous properties that we didn't have before because we joined together. And when we looked at it, we were essentially about a ton molecular weight, averaging about 150 for each of us. And so that's really what polymers are, is they get you to that very high molecular weight from very small units that have tremendously different properties. And in fact, polymers usually don't start to exhibit the really cool properties till they reach molecular weights of around 10,000. And a little tiny ethylene molecule, two CH2s hooked together, is only 28 in molecular weight. But that can come together in order to get up to those kind of molecular weights. And then you get these beautiful properties of polymers. So that's a little introduction of what polymers are and really what you're calling plastics are. So here's a great reference. This was by Roland Geyer and Jenna Jambeck and Cara Law, and it's really a pivotal document. In fact, it formed the basis for another really unbelievable document, which was published in National Geographic on plastics and the planet or plastic. And it was almost saying that we've got to start deciding what's going to happen to our planet because of the plastics. But it all came from this work where they really looked at what's the magnitude of polymers. And the polymer and plastics have really grown from 1950. It was really post-World War II when we discovered bakelite, we discovered cellophane, early on. But it was really after World War II that we really started to grow plastics and polymers. And so it was only 2 million tons in 1950. It grew to 380 million metric tons in 2015. Those are yearly amounts. The compound annual growth rate was almost doubling what the average growth rate of the society was at about 8.4%. And when you look at it on a cumulative basis, 8,300 million tons of resins and fibers, and those included polyester, nylon, and acrylic fibers in 2015. This study went through 2015. It was published in 2017. And about half of that came from 2004. That shows how fast it was growing. I'm going to show you a little bit more about what this polymer growth and plastics growth looked like. So this is from the perspective of where are these polymers going? What kind of applications are they going in? And this sort of sums it up from packaging to transportation, building, electrical, consumer, industrial machinery. So actually being used in industrial machinery applications, and in the fibers being used in textiles. And you can see that that bottom one is packaging, and you can see how huge that is. That's about 40% of the total. That's where most of the polymers end up in application. The other one that's really big is building and construction. And that's mainly due to these guys, PVC pipe that goes into building and construction. And then another one, the other two that are consumer institutional products, toys, all the kinds of things, devices that we use in consumer products. That's that light blue. And then in textiles is the fibers. So when you look at it, what kinds of polymers are making up these areas? And they almost track, you know, similarly to what the applications were, because we still have on that lower right part of that curve, you see things like low density polyethylene, linear low density polyethylene, and high density polyethylene, and then polypropylene. But that red and the orange in the bottom, they're both polyethylene. Polyethylene turns out to be the most produced material in the world. And it, unfortunately, it comes from fossil fuels, and unfortunately requires high temperatures and pressures to make it, which both of those release greenhouse gas into our atmosphere and are big contributors to greenhouse gas emissions and climate change. But why? Because the thing that's amazing about polyethylene is, in those factors, look at the products it can produce with just those different types. So a garbage bag is really flexible. That's low density polyethylene. A water jug is nice and rigid, has great properties. That's high density polyethylene. But look at high density polyethylene. You have a grocery bag, you got to be able to hold weight. That's also high density polyethylene. You got a rigid container that's got to have good resistance to chemicals or things that are put into it. That's also high density polyethylene. It is so versatile that it can find these different applications. All the same molecule, changes in the way the process develops that molecule. I told you about all of my students hooking together in the molecular weight that comes together by how many of those monomers come together and how they come together. So polypropylene is that lighter orange color. That's also found in lots of articles. Polypropylene has the really neat property that polyethylene doesn't have, even PET doesn't have, that it has much better thermal properties than polyethylene or PET. So you can put these things in a microwave. These can be your Tupperware containers that are polypropylene. Can also be making plastic cups out of polypropylene. And then the other one that's up there, it's in pretty, well, the polystyrene is that little light blue one. And polystyrenes also can be used in cups, in lots of articles, toys, and that kind of stuff. Polystyrene has an issue in that one of the materials used to make it, styrene, is a suspected carcinogen. So it has some issues about the materials that go into it. And then PVC, as I mentioned, that's what's in the pipes. And that coupled with polyethylene, and PET, which we're going to come to, those are probably the biggest plastics, the biggest volume plastics that are out there. So PET is that next.
Ross, you went to mute. Ross. Somehow you're muted. Anybody else muted?
There you go. Sorry. I just saw that. Yeah, so PET is finally rounded out as the next really biggest one. I think everyone knows where PET is. That's in the PET bottles. They're huge. Between Coke and Pepsi, just looking at water and soda bottles, you're talking about combined over 70 billion containers a year. It's huge. And then PET is also, it's very versatile, can be thermoformed into nice containers for produce. And it's also used in Mylar film. So labels, balloons, those are all made from PET. So you can see the enormous volume because of the versatility of these materials to serve us in just great functionality for the things that we want in our livelihood. Let's see. So let's talk about the circularity challenge. So as I'm sure you took away from Karen's talk, this linear process of where things are going into not being recycled for all the different issues that are associated with trying to establish a recycling system. It's because we're basically in a linear system today, which is usually referred to as take, make, waste. So this just shows what that 8,300 million metric tons looked like in terms of starting from 1950 through 2015. All cumulative, we had about 8,300 metric tons, million metric tons produced. And in use right now is 2,500. So that means that things like that PVC pipe, this is in an application that's going to last a long time in a building. So it's still there. Some of them may still be there. And then what happens to it though is the things that get discarded, almost over half of that has been discarded. And that represents waste, either in the environment or in landfills. About 800 million metric tons have been incinerated, and about 600, or only about 9%, have been recycled. And that's the extent of circularity we have today. That's the challenge. And as Karen's system mentioned, how do we bring that recycling system into our heart and redirect those things that are going out to the right into the environment? Incinerating is not a good thing, even though we even capture some energy from it. If we're releasing that carbon that's been fossilized, from most of these things are coming from fossil fuel sources, now we're releasing carbon up to the atmosphere. It had been sequestered. We're adding to that carbon dioxide concentration in the atmosphere, and that's causing our global warming. So that's not good. So we'd like to be able to bring that back as in Karen's type of system to have a circular system rather than a linear system. Okay, so let's look at some examples and see what's happening. So I'm going to talk about 3 examples. One is electronics. So if anyone were to ask you, what's the top challenge in electronics? It's miniaturization. How do we keep making these things smaller? Look at how flat they are. I remember the first mobile phone I had. It was a big, thick mobile phone out of Motorola. It was about that thick, much higher. We keep making them smaller. How do we make them smaller? And Moore's Law from Intel, they saw the trend, and they actually established that we're going to double the density every 2 years, and that's what they were doing, and they continue to make it happen. It's essentially putting more and more transistors in smaller and smaller space, and they've been able to do that every 2 years. It's almost getting to the point now where we're at the molecular dimensions in order to store things. So how do we do that? What are the kind of issues we face, and what is so important about polymers in helping us face those issues for electronics? So it's really making things very, very small. And so a key electronic component that uses polymers, the valuable properties of insulation from polymers and their dielectric properties are capacitors. Capacitors are huge. They're a fundamental electronic component. So how do you make capacitors smaller? And in the old days, people might remember like capacitors, they're actually metal leaves and they had air between them. Well, now we can make them with very thin films. And we just metallize that film and roll it up, and we have a capacitor, conductor, insulator, conductor, insulator, conductor, insulator. And these are how small they are. Look at the dimensions there with the eye of a needle. And at least the lead of those capacitors can easily pass through that eye of a needle. That's how small we're getting. How do you do that? We look at polymers that have good dielectric properties. The PET I talked about, the same PET type of molecule that goes into those bottles, great insulator. It's used in capacitors. PEN is a special kind of PET rather than terephthalate. It has naphthenoate as one of the monomers. That also has great dielectric properties. Polypropylene, all excellent, all used in capacitors. The metallizable means that they can be vacuum metallized, and you need the conductor. Conductor, insulator, conductor is a capacitor. And thin. So how thin can we make it? We know how to make films. How thin can we make that polymer film to be able to miniaturize? Typical PET films for capacitors, the thinnest is usually around 1.5 microns, and they range up to 6 microns. That's pretty thin. A human hair is on the order of 70 microns. Mine is really thin. It's 20 microns. This is just on my hair. This is about a third of the thickness of one of my hairs, which is already about half the thickness of most other hairs. So very thin. But that's good enough to get the breakdown voltage resistance that's needed in that range. And how do we get films that thin? So what's done, and this is where all the years of really understanding these tremendous properties we got by building these big molecules pays off. And so this tremendous established knowledge and infrastructure in order to make beautiful properties out of polymers and what you're calling plastics. So you need something that's thermoplastic that can be melted. That fits all the bill for the ones we talked about. PET, PEN, polypropylene, polyethylene, polyamidous nylon, they're all thermoplastic. Means that when they heat, thermal means heat, plastic means flexible, gets flexible. Heat can be drawn, can be flexed, heat more, actually can be melted, can go back in and reclaimed and brought back into its same properties just by cooling down. So this is really cool technology. This was technology that DuPont was involved in, and it's building a simultaneous production line that can stretch the polymer film. So it comes in, and actually DuPont makes the polymer. They actually bring monomers, those little guys, right into the plant for the film. They make the polymer. Right after they made the polymer, it goes right continuously right into a film line. And as that polymer is melted, it's cast first, and then that cast line is stretched. It's heated above its glass transition. That's what gets it plastic, being able to start stretching it. And it's stretched both in the transverse direction, the width, and in the machine direction, the length. And what they found was, what DuPont came up with was a way to do it really smoothly. Because if you can do that really smoothly, you don't have breaks. And you can continuously have a web. And so what they did is, anyone who's taken a bullet train, they have linear motors. Normally in a motor you have a circular field that generates a magnetic field. In a linear motor you generate, the magnets are linear, and so you're pulled along in a linear direction, not in a circular direction. So it's a linear field, magnetic field that's pulling in the linear direction. And they use that, it's very smooth. They build linear motors that just pull that very smoothly, just the way like a bullet train rides very smoothly. And they use that force in order to move the clips and move and stretch the film. so smooth that they can go very, very thin. Stretching builds properties into the polymer. So as you stretch it, it's orienting those polymer chains. All my students hooking together, well, it would turn out that they would orient them so that if certain students had ways that they could assemble in being with unique, maybe other ways that they connected with each other to form pockets of associations, that they didn't come apart, that being together meant something really important for the structure. That's what crystals are. Crystals come together with unique properties from their associations with each other. And so what happens when you stretch is that the polymer chains align to find those regions where they can essentially form crystallites. And that offers tremendous properties. It helps barrier, it helps thermal properties, it helps toughness, which is modulus. So stretching orients, crystallizes, gives great properties. Great properties mean strength, modulus, so enables very thin films to be formed. So the question then is, how thin can we go? So when I was at Circleville Mylar plant, and we were we just gotten hold of this technology, built a pilot plant with this technology. We're making thin films. So being the leader of that, I challenged our team. I said, what's the thinnest film we could make? How thin can we go? So if I had more time, I'd ask all you to take guesses on it. But I'm going to show you and tell you the answer. And this remains as the world's thinnest polyester film. We made the world's thinnest polyester film at Circleville in the Mylar plant. We never commercialized this because it was on the outer limits. I mean, you would never commercialize something at your finest edge. We did commercialize something very close to this that had more tolerance associated with it. But the world's thinnest polyester film looks like this. And if you can see it, if I just hold up in that light, you can see a little bit of a rainbow effect. I think you're starting to see a little bit of color in there. In fact, if I let it go, it will start to float. And it clings to my hand. It's got some color effect. But look how cool this is. Something that thin is wound up in a roll, just like Scotch tape. And this is just a combination of it, but there it is. This is, our humidity is low here, so it's clinging because of the dielectric properties of polyester. But
Ross,
this is it. It's wound up.
Ross,
And yeah.
we're gonna have to keep moving. We got about 10 minutes.
Okay, I'll move through. 300 nanometers thick. So this is actually nanoscale, 0.3 microns, 300 nanometers thick, thinnest polyester film ever made on that first linear motor simultaneous stretching line. And this is a new Bruckler line that just came out using that technology. The technology was licensed to Bruckner, and now they're even talking about could they use that to improve the crystallinity of polyethylene. And that's used in so much packaging. And if you did that, maybe you wouldn't need to have all these other multi-layers in packaging if you could build in really good properties in polyethylene as a single layer. So just wanted to touch on two other areas. I'll do it quickly. The carpets, those are the top challenges. I think everyone can identify with that. Existing carpet materials, if you've gone out and looked for carpets, usually you're faced with, should I buy a polyester carpet or should I buy a nylon carpet? Polyester is the same type of polyester that's used in the bottles, doesn't wear as well as nylon. Nylon doesn't resist stains as well as polyester. So you're usually trying to make a trade-off. Both of them have that good soft feel for carpets. So along comes this molecule, different type of polymer, a little different, has an extra carbon atom, in one of the monomers versus the PET. And this one has good wear, good stain resistance, good feel, and so it's combining the best of PET and nylon. Wouldn't that be great? You don't have to try and make that trade-off. But there was no really good conventional route to manufacture. So what had to happen, they actually found there's a better way if they can learn from nature to make it. And what they did is they actually genetically engineered an E. coli organism in order to produce one of the monomers. So rather than feeding sugar into an E. coli and having it just respire and generate energy and reproduce from it, they actually genetically engineered it to produce 1,3-propanediol as one of the monomers for this material, this polytrimethylene terephthalate. This is the kind of science that went on. The E. coli has that number of genes. They had to make 33 gene edits, 10 biological pathways had to be altered, and they wound up with yield better than the chemical method. And they built a plant that's over 100 million pounds a year. It's been expanded once in order to produce this carpet. Packaging, the top challenges in this area are you gotta protect the packaged goods, have to be able to enable the delivery to the user, and you don't want it to exit in that area that it contaminates the environment. You want to have it somehow be closed loop, leave a negative impact on the environment. So this was just looking at different types of packaging. By far the largest area that would, when I went back to that first thing I was talking about in my talk about the 40% of all those polymers that are going into packaging, most of it's out of PET bottles and flexible plastic. So we could find a way to improve those. We'd go a long way to helping keep the plastic out of the environment. And so here's an opportunity to use a natural material as a plastic. And this material is called Thermoplastic Starch. And it comes from a little company in Australia, Plantic. It's now part of Circularity. But what they found was a way to refine starch. So it got rid of a branched polymer that when you normally think of starch, you think of the paste, the white powder, you make paste with it. That's coming from amylopectin, which is branched, which doesn't have good film forming properties. But the other part, the high amylose part of the starch, has great film properties. And so they were a way to find a way to make the starch with that high amylose. And that's thermoplastic starch. Still could be eaten, it's still completely edible. But the cool thing about it is that if you take a little bit of water, so this is what the candy tray looks like, really, really cool. Nice properties, it's been thermoformed. Got 2 trays here. You can put different colors in it. Obviously you want to make sure that you put it with a nice food edible dye or something. It's not toxic. But then if you take, so I just took a little piece of that candy tray. And if you take water, and this is water. I could drink it just to show you it's not acetone. I put a little bit in there. And we'll just let it sit for a second while I go on and tell you a little bit more about this. So this is completely renewably sourced. It's coming from, it can come from lots of sources of sugars. It could even come from cellulosic by being converted by enzymes back into the sugars. Completely degrades on contact with moisture. We'll put this to the test right now. Fits all of the compostable, home compostable, it's even flushable. It's a life cycle analysis has been done. It shows that it's 60% less energy, greenhouse gases than what it replaces, which is typically the fossil fuel-based polymers like polyethylene or polystyrene. And it's excellent properties in low water activity applications. So it can be used in candy trays, chocolate candies that well through low water activity. It has great anti-static properties, so it can be used to package electrical goods, but can be used in nice applications for secondary packages. A lot of times you'll find if you were buying a pacifier for an infant, it's always packaged in a secondary container. And that secondary container typically is polystyrene. I mentioned styrenes are a potential carcinogen. Why would you want a pacifier packaged in something that might have little traces of a potential carcinogen monomer associated with it? So here is a pacifier packaged in the secondary container of thermoplastic starch, which you could eat if you wanted to. And I think we're just being able to maybe see something breaking through here. Yep, there it goes. Everyone see that? Just went through. So I don't know, Chuck, if you're recording the time, but I don't think it was much over a minute. But
No,
here,
it wasn't much over a minute.
here's the water that's in the little tray. And here's the beginning of this completely dispersing, where we'll leave zero footprint. Microbes will now convert this to carbon dioxide and water. And well, you can see that little, yeah, you can see it. There it is. The little hole that just started there. Now we'll just continue to disperse. Very much like the PVOH that Monosol makes for your dishwasher tabs packaging that dissolves in hot water, just dissolves in room temperature water in less than a minute. But makes perfect
Ross,
film.
we should finish up so we have some time for questions.
Yep. So that was next to my last slide. So just where are we going? Renewably sourced feedstocks or polymers. I showed you the one for the PTT. Also looking at it for PET. That bottle I used, partially renewably sourced. There's going to be ways to make it 100% renewably sourced. We've got a PhD student who's doing renewable sources for phenolic resins for aircraft composites. And remember that beautiful line, using the downstream recycling infrastructure. When you change the feedstock to renewable source, everything downstream of that stays the same. So you can take advantage of all that wonderful knowledge that we've built over the years. Naturally degradable polymers that become part of the environment at the end of life, like the thermoplastic starch. Enzymatic biorecycling. Enzymes are specific to molecules. Let's find some enzymes that can break apart a thing like a composite or polymer, bring it down to the small units that can then be repolymerized and used again. And then there's all neat ways to do things around manufacturing, like 3D printing, like self-assembly via micelles. And then IBM's got a whole program to use quantum computing to actually calculate how to make the best synthetic process or manufacturing process. And then things that just reduce material intensity, using foams, using air, being able to just reduce the amount of materials we use. That's basically where we're going to be headed. It's an exciting future. We have a way to make an impact. So thank you so much. Sorry I took it.
Thank you, Ross. Thank you very much. Thank you, Karen. Also, the floor now is open for questions from the audience. And you can either provide the question in the chat or
I'll stop sharing.
directly. We there? Hello?
Yep, you there.
Okay. Joe, do you have a question in the chat? Hold on a minute.
I have mine.
Okay.
So alluding to the pacifier as an example, and this is very general, so do plastics or products made overseas and sold here in the United States fall under the same safety regulations as if they were made in the United States? And again, using your pacifier as an example, is it required that that pacifier be packaged in a safe, non-carcinogenic, non-chemical leaching package? Does that make sense?
Yeah, so so to answer the question, we did this. So we actually partnered, when I was at DuPont, we formed an alliance with Plantic. We brought that product into the US. This was one of our customers, so we brought that to them, and they did replace their polystyrene with that as their new container for the pacifier. everything, even though we were bringing it in, and we actually put it on as a DuPont product, but made it a DuPont product, we still had to meet all the requirements, even though it was manufactured in Australia. We had to meet all the requirements in the U.S. So I think to answer your first question, yes, it has to meet all the requirements in the U.S. To answer your second question, I don't know if what the requirements were in terms of allowing pacifiers to be packaged in polystyrene. Polystyrene is used in tons of secondary packages, and so so I was throwing it out as a concern, but it probably passes the limit that's placed on potential analysis of in Headspace or however they decide to test it for residual monomer coming from polystyrene. It's probably very low. It's just that you have that possibility.
It's not zero. The point is it's not zero.
Yeah, but good question.
Okay.
Yeah,
Karen, there's a question here in the chat for you. Can you hear me, Karen?
Yes.
Oh, good. Okay. So the question is, during your research, did you find a specific region of the United States that had stronger recycling systems and was more proactive than other areas of the United States?
So that's a great question, and it's really interesting. And I think one of the greatest sources of data on that was Waste Management, which is one of the largest waste management providing companies in the U.S. They just released data in September showing where all of their different material types are coming from and being processed. And what's really interesting is how it differs. So in the southeastern United States, most of the recycled content there is going into industrial or different processes that aren't like back into packaging. So going into potentially carpets or decking because there's a lot of processors in that part of the US. Whereas in some areas, and especially in states that have bottle deposit programs, so where you can turn your Coke bottle back in and get 5 cents for it, those states have really clean supplies of PET that can be used for food grade applications, so can be turned back into bottles. And so in the Northeast, there are several states that have those in place. And so those systems are really working in terms of getting that type of recycled content back into new packaging instead of into different end applications. The same is true over in California that has a pretty clean stream in terms of the PET for bottle deposits. And so it's really dependent on where the manufacturers are that process those recycled content and then also the way that it's being collected in different areas of the US.
Okay, thank you. I'm looking to see if there's another question here in the chat.
I have a question, I think it was from Sean here, that just asks for a clarification on advanced recycling technologies. And so one of the things I will point out is the last thing that Dr. Lee mentioned, or one of the last things, that enzymatic recycling is an example of advanced recycling. And so it used to be referred to as chemical recycling because there were chemical processes such as pyrolysis or gasification that break down the plastic waste. But now there are some that aren't necessarily dependent solely on chemicals. And so it's kind of expanding the term of what advanced recycling actually means. And there's a lot of different new and proposed technology that's not at scale yet, but really working to address some of these needs by actually breaking down the polymers into the component monomers or into different oligomers, different pieces of those polymers.
Yeah, I've got a question from Melissa. I'm not sure if I pronounced your first name right, but are there considerations in the depolymerization process causing eutrophication when entering waterways? And so I would say in the intentional depolymerization process, you actually are trying to collect those materials and make sure they're part of the new system to bring them back into the process to be repolymerized. So you're really guarding against that, letting out the monomer go into the environment. So And the ones that are naturally occurring, if it's carbon dioxide and water, then those things typically would not be hurting eutrophication. And Karen, I don't know if you have any thoughts on that one too.
No, I think that's a great question to consider the whole life cycle impacts of even if something is biodegradable. Also understanding that biodegradable doesn't necessarily mean that it's compostable, and so understanding the impact it might have if it's in a different conditions. And so I think it's a great question, considering not just whether it can break down, but what happens to it when it breaks down and what's the effect.
Yeah, and that could be important, especially eutrophication with a means of nitrogen compounds. If you had something like a nylon breaking down in an uncontrolled way, not an intentional way, like biodegradation, so that could cause eutrophication. That's a great point.
So in the latest C&E news, there's a demonstration plant in Norway. They're kind of way ahead of us in this whole recycling. Europe makes some major advances at the demonstration level. Done pyrolysis on plastic feedstock and gotten to the point where they're feeding 500 tons of this plastic to their refinery for basically processing as a feed oil, as a feedstock into new petrochemical processes, new petrochemical products. So I think Europe is actually quite a bit further ahead from the US in their percentage of plastics that they're recycling and the mandates they're putting in place to deal with this problem.
Yeah, I think one of the big things when I mentioned having no real policy in the US that addresses it is when you look at the EU, they've had some form of extended producer responsibility in many EU member nations for almost decades in certain areas. And so you can really start to see that some of those programs and those policies really do encourage recycling and incentivize it and incentivize actual producers to take back that material and then be more conscious about what material they're putting out into the market.
Any other questions?
Yes, Chuck, this is Carl Grunwald, and I'd be happy to ask a question.
Sure.
First, I really enjoyed both of your presentations, Karen and Ross. They were fantastic. And one question I had for Karen is, with all the data that you assembled, it really struck me how you were able to gather so much data and put it together and use that STEEP analysis and the assessment rubric. And I just wondered if you've looked into using that rubric to analyze other things besides plastics, and if there's opportunities for decision making around that rubric when comparing different things.
Yeah, that's a great question. I was fortunate to be able to talk to different master's students that were also working on projects and kind of share that with them to start to plant the seed to maybe use it or that similar type of methodology to assess a different system. And so I think the way I designed it was to be able to apply, nothing in the rubric is specific to plastics. And so you could technically apply it to any system. And I think that would, the more that methodology is used, ideally it would be refined to be more objective and take, the subjectivity out of it. But also, again, be able to compare different systems and see where they rank. And then I think that it would be great to, especially to take the STEEP approach, maybe not necessarily that STEEP approach, but a STEEP approach for decision making to be able to really assess a system and really consider, where the trade-offs are and not just look at it from, what economic benefit it's going to be or what environmental issue it's causing, but really take the whole system into account when making decisions.
Right, like even like government policy, things along that line.
Yeah, I think there's a great application for that.
Thanks. And just also for Ross, I live in a community where we have this large recycling dumpster. And I noticed that over time, there seems to be very little or no recycling of glass. And I guess glass has been replaced by plastic. I guess I was just wondering if you might have any insight on on what's happening to glass. It just seems to be disappearing.
Yeah, absolutely. I mean, the big growth in PET came at the expense of glass. Started with the 2-liter bottle where breakage was a big safety issue, and then it extended into the smaller bottles. And that I mean, that's mainly the key was safety around the breakage, glass breakage. So glass has been largely replaced in packaging by plastic and PET. Other polymers as well for the safety and also for the weight and transportation savings. So that's why you're seeing so much more plastic than glass. There is still glass out there, and there is still glass that's being recycled.
Any thoughts, which is easier to recycle, glass or plastic?
The clear glass is probably easier to recycle. Most glass manufactured today has recycled content in it. It's the cullet, as they call it, actually lowers the melting point, makes it easier to process, easy to melt. So most glass has recycled content, and it's a pretty well established process. That system, going back to what Karen mapped for polymers, is actually more established, much more established than it is for polymers. So I would say glass is easier to recycle when you're defining recycle as actually getting it into a product and actually seeing it in the product, recycled product.
Thank you very much.
Sure.
I have a question for, I guess, Karen. How much of the recycling problem, if you can tell, is driven by the fact that virgin resin is so low cost?
That is definitely a huge factor because there is little incentive outside of, pressure and environmental considerations to really transition to using recycled resin, PCR resin coming in. If you're given a lower cost option with the virgin material that has better quality and potentially higher properties, then that for the most part is going to be, the ideal choice for a manufacturer, because a lot of the recycled resin has contamination or just weakened properties that don't make it as high quality or as high performing as the material. So that is a significant impact, and it's kind of fed into by a lot of other parts of the system, like the fact that there are subsidies on a lot of that type of material coming in as well, and so there's it is an uphill battle for recycled content, especially if there are no policy levers or economic levers to increase that. But also a big part of it is increasing the quality of the material coming into the recycling system by reducing contamination, and then also increasing the quality of the output by improving mechanical recycling processes and improving advanced recycling processes as well.
Thank you. Do you, as a follow-up to that, have you looked at other countries and their systems of recycling plastics, and is any one country that stands out as doing it well?
Yeah, so I think for the scope of my project, I really focused on the US because I wanted to see what the impacts were, especially post changes in the export policy. But so much of the literature is coming out of Europe because, like I said, they've been really kind of ahead in terms of different policies and technologies. And so they're, especially, I think, one of the first EPR systems went into place in Germany. And so Germany has been pretty high. And I think a lot of the Nordic countries as well have high recycling rates and I think really because the EU is so interconnected, there's a lot of higher rates and improved technology that's coming out of the EU. And a big factor there too is limited landfill space. So it makes a lot more sense to recycle when you don't have a big area of land to build a landfill and to throw trash into. So that's been a thing too. And I think Japan as well is just another country that has been doing recycling pretty well. Those are some of the ones that come to mind, I think.
There's a question for Ross. In your growth chart, Ariel noticed that there was a spike and a drop within 2005 to 2010. What caused that?
I'm thinking that's probably around the 2008 issue that where the economy tanked, and so that affected volume and production. That would be my guess.
Okay. And here's another question, I think, perhaps for both of you. Should, relative to some of the standardized sizing like lids, size, and shapes of bottles, has there been any action in that area to try to make things more compatible and consistent and standardized relative to containers?
I think there has. I used to do a lot of work with Alcoa, and is now CSI for closures, and they always tried to do that. So that, I mean, and that in terms of materials, the closures are typically made of polypropylene, and that's there's a reason for that, and that's to help recycling. When you put polypropylene, which has a density of 0.9, on a PET bottle, which has a density of 1.3, you grind it all up in order to recover the PET flake, which is the heavier part of the mix. The lower density polypropylene floats up, and so it allows you to separate them out. And there's been uniformity on that. So even staunch competitors like Pepsi and Coke still have standards in terms of the material for the closure, and also dimensions for the closure, so they can take advantage of huge volumes and machine designs for making those.
Yeah, I would agree. I think in terms of more so not standardizing sizes and shapes, but standardizing material and getting to similar, monomaterials that aren't all of these different layers of polymers that make it really difficult for an item to be recycled. The other thing, especially in packaging, is to think about the entire packaging system. So if you have a bottle, a lid, and a label, making those all the same polymer, at least as in the same family, so that they can be recycled together. That's kind of a trend that we're seeing, like moving towards being able to design products for recyclability, understanding that the mix of materials matters, and then the format, film versus rigid, matters, and so taking that into consideration when products are being put out on the market.
Any other questions?
Yes, here's another one for Karen. The Circularity Challenge slide, are the quantities shown production at 8,300 on a per annum basis?
I think that was.
I think that's for me. Yeah, that's cumulative.
Cumulative, okay.
That's from 1950 to 2015. Annually, it's about 380 million tons. In 2015. And it was growing about 8% a year.
Any other questions?
I have a question. Since plastic is always going to degrade each time it is recycled, how can it really be considered a circular material?
So that's a good question, and it really actually depends on the type of recycling process. When you think about mechanical recycling, those polymers are being shredded into a new material, or shredded into that recycled resin that can then be melted down, and potentially, or in mechanical recycling, it is being degraded. But when you look at some of the advanced recycling technologies, what those actually are doing is breaking the polymer down into a building block, and that building block can then be used to make a completely new polymer. And so it's not necessarily being degraded. However, in that situation, you have to look at the efficiency of how much of that original material is then becoming those building blocks, and what percentage of it is going to waste or to fuel or to some other application. So it's potentially not being degraded, but there are losses within the system. So you're right there right now, not that I know of, there isn't anything that takes it and completely keeps everything in the system, but there's a lot of efforts, I think, working towards doing that, so that with the goal of it truly being circular and maintaining all of those, that base material within the system.
I had a question from Alan. So Alan Johnson, is there any research to make plastics an efficient fuel? Why is it so hard to burn plastics cleanly? So actually there is research where they do pyrolysis of plastics and take them down to not all the way to the monomers, but to oligomers that can be used as fuel. People get excited about that, but I have to tell you, that's not such a wise thing to do. If you're doing it from fossil fuel-based polymers, all you're doing is making more fossil fuel-based fuel, which when you burn it, it creates more carbon in the atmosphere that leads to greenhouse gases. So it can be done. What's a much better thing to do is to use the same process, and they're looking at this. Polyolefins are typically kind of hard to depolymerize and reuse the monomers because they're gaseous. It's hard to break it down and be able to get the nice, pure, very low molecular weight monomer. But if they can get it to an oligomer or smaller, that then can be fed back into their production unit for making the polyolefin to begin with, and they have crackers in there that can change that oligomer get it ultimately to the monomer. That works nicely, and now it gets it back into the polymer itself. So breaking it down, what could have been used as a fuel, but rather than using it as a fuel, bringing it back into the process to make more polymer, that's a wiser thing to do. And SABIC is one company that's doing that.
Any other questions? Okay.
You want to wrap, Tom?
Yeah, no, you can if you'd like, Charles.
No, go ahead.
Well, first of all, Karen, thank you very much. And Ross, thank you very much. It was very, very interesting, very informative. I'm sure you could probably talk about this for hours. There's such a huge problem, and we're glad you're working on it. So thank you very much. And thank you, everybody, for joining in tonight.
Thank you all. Thank you all for the opportunity.
Yeah, thanks for having us.
Thanks so much. Really appreciate it. Okay.
All right.
Have a blessed
Bye-bye.
night. Stay
Everybody
safe,
have a good
everyone.
evening.
Take care.
Take care. Nice seeing you again, Karen. Take
You
care.
too. Take care.
Thanks so much, Ross.
Thanks, Chuck. Thanks for the invite.
Really appreciate your effort, and I know it's a very, very busy time for you, so I really thank you so much.
No, my pleasure. Thanks. Take
Thanks,
care. Have a great
Ross.
night.